Hello, in this lecture we'll answer two questions. In the first question we find out the area of this green shape using two different methods. And the second question we will find out the area of this circle that intersects with this right triangle ACP. So we start with the first question. In the drawing we have a quarter circle, AOB is a quarter circle. This is side OB. This equals to 2 units in its length. In addition, we know that line 7 AD equals to line 7 DO. And our task is to find out the area of this green shape. The green shape is actually the right green triangle DCB. So we have to find out the area of this green right triangle DCB. So first of all, we know that AOB is a quarter circle, and therefore angle AOB is a right angle. In addition, because of the fact that AOB is a quarter circle, the two on the area of this quarter circle are AO and OB. But the radius OB equals to 2, and therefore the radius OA must be also equal to 2 units in its length. This is the radius AO of this quarter circle. That equals to 2 units in its length. This is point D. Point D is the midpoint of the radius AO. That is to say, at point D, the radius AO has been bisected into two halves. The first half is AD, and it is of course equal to the second half of the radius AO, that is DO. So each half must be equal to the radius over 2. So the first half AD equals to the radius, that is 2, and 2 over 2 is 1. Likewise, the second part of the radius, the second half of the radius AO is DO. That is of course equals to 1 unit in its length. In the next step, we will implement the Pythagoras theorem on this right triangle DOB. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle DOB, here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle DOB, dB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. And again, according to the Pythagoras theorem, on this right triangle DOB, dB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. dB is the missing hypotenuse, so we leave it as it is, so it is dB squared equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 4. So in total, we should now know that dB squared equals to 1 plus 4, that is 5. So dB squared equals to 5. Here, we will take a root out of this equation and find again that the missing hypotenuse dB is equal to the square root of 5 units in its length. The length of this hypotenuse dB is equal to the square root of 5 units. In the next step, we will do a construction. That is to say, we will complete this quarter circle to a circle. So completed this quarter circle to a circle, and we'll extend the radius BO by a straight line until it touches the circle. The radius is a straight line. When you extend a straight line by straight line, the result must be a straight line. So we define the touching point of the extended radius BO with this circle. This point is point P. Again, we extended radius BO by straight line, and therefore the result BP must be also a straight line. So BP is a straight line that touches the circle at 2 points. Those 2 points, P and B. Therefore PB is a chord. PB is a chord that passes from point O, that is the center of this circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. And therefore, PB is the diameter of this circle. So, moving on, PB is the diameter of this circle. PB is the diameter. In the next step, so point O is the center of the circle, point P is the point on the circle itself, therefore OP is the radius of this circle. It equals to 2 units in its length. We will extend the radius AO by a straight line until it touches the circle. And we define the touching point of the extended radius AO with this circle. This point is point Q. So actually AQ is also the diameter of the circle because we extended the radius AO by a straight line, and therefore when you extend a straight line by a straight line, the result AQ is also a straight line. AQ is a straight line that touches the circle at 2 points A and Q, and therefore AQ is a chord. AQ is a chord that passes through the center of this circle, that is point O, and therefore AQ is the diameter of this circle. Point O is the center of this circle. Point Q is the point of the circle itself, therefore OQ is the radius of this circle, that equals to 2 units. In the next step, we will extend side CD on this right DC B, we extend side CD by straight line until it touches the circle. But the question is where the extended side CD will touch the circle. We will assume that the extended side CD will touch the circle at this point N. Therefore, we have here triangle BCN. So this is triangle BCN. That is equal to 90 degrees inside according to what is given in the question. And the triangle BCN subtend on this chord called BN. But chord BN is definitely not the diameter of the circle because of the fact that chord BN doesn't pass through point O, that is the center of the circle. So if a chord doesn't pass through the center of the circle, it cannot be the diameter of the circle. So we have here triangle BCN that is equal to 90 degrees inside, and it subtend on chord BN that is not the diameter of the circle. So it is a contradiction to rule 5. So let's click on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees inside must subtend on the diameter of the circle. In the drawing circle, MN is the diameter of this circle. This is triangle MAN is equal to 90 degrees inside, and according to this rule, rule 5, triangle MAN must subtend on the diameter of the circle. And indeed, triangle MAN subtend on chord MN, that is the diameter of the circle. So according to rule 5, any peripheral angle that is equal to 90 degrees inside must subtend on the diameter of the circle. We have here triangle BCN that is equal to 90 degrees inside, and it doesn't subtend on the diameter of the circle because BN is definitely not the diameter of the circle. So due to the contradiction to rule 5, we will conclude that the extended side CD cannot touch the circle at point N. In the next step, we will assume that the extended side CD will touch the circle at this point M. Again, we will assume that the extended side CD will touch the circle at this point M. So according to our assumption, we have here triangle BCM. This is triangle BCM. This is equal to 90 degrees inside. Triangle BCM subtend on this chord called BM. Chord BM is definitely not the diameter of the circle because of the fact that it doesn't pass from point O, that is the center of the circle. And because of the fact that chord BM doesn't pass from point O, that is the center of the circle, chord BN cannot be the diameter of the circle. So we have here contradiction to rule 5, because we have here triangle BCM that is equal to 90 degrees inside, and still it doesn't stand on the diameter of the circle because of the fact that chord BM is definitely not the diameter of the circle. So due to the contradiction to rule 5, we will conclude that the extended side CD cannot touch the circle at this point M. And therefore, we have to conclude that the extended side CD will touch the circle at point P and not in any other point, due to the contradiction to rule 5. And again, we found out that the extended side CD will touch the circle at this point, point P. Now we don't have contradiction to rule 5 anymore. Why? Because we have here peripheral BCM, this is equal to 90 degrees inside, and peripheral BCM, some set on chord PB, this is the diameter of the circle, exactly according to rule 5. So in this right triangle, DPO, point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle, equals to 2. DO equals to 1. We already found out that if a right triangle has two perpendiculars with 2 and 1, then the hypotenuse must be equal to the square root of 5 units in itself. And therefore the hypotenuse of this right triangle PDO must be also equal to the square root of 5 units in itself, because those two triangles are identical. PB is the diameter of this circle, and therefore it is absolutely a straight line. So if you focus on the upper side of the straight line PB at this point, point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is the right angle, plus this missing angle, in total the sum of those two angles must be equal to 280 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Actually, first of all, I have to prove that this is a right angle, and because of the fact that this is a right angle, triangle PDO is a right angle, and therefore I can implement here Pythagoras theorem. And according to the Pythagoras theorem, the hypotenuse PD must be also equal to the square root of 5 units in itself, because those two right angles can go into each other. PO equals to OB, the above the radii of the circle is equals to 2, and therefore they are equal to each other. And those DO is the common side that belongs to both triangles. And finally, those two angles, they are both right angles according to rule 3, and therefore they are equal to each other. So those two right angles can go into each other according to side against side rule. And therefore, those two corresponding sides, that is to say DP and DB, must be also equal to each other in their lengths. According to the rule, the corresponding sides that can go in triangles are equal to each other. But DB equals to the square root of 5, and therefore its corresponding side, that is DP, must be also equal to the square root of 5 units in its length. So here we can implement rule 24 in our drawing. So I repeat quickly on rule 24. According to rule 24, first of all, rule 24 is drawing any circle. In any circle, if chord AB intersects with chord CD at point O, then the following equation is told that AO times BO equals to CO times DO. In the drawing circle, this is chord AB that intersects with chord CD at point O. So in this drawing, so whenever you have two chords that intersect with each other inside the circle, then the following equation is called that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 24 in our drawing. In our drawing, this is called AQ that intersects with chord PB, and this is called AQ that intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. So all the requirements of rule 24 are satisfied, and therefore we can implement here rule 24. So until now, chord AQ intersects with chord CP at point D. Intersection point occurs at point D. And again, chord AQ intersects with chord CP, it's point D. So all the requirements of all 24 are satisfied, and therefore we can implement here all 24. According to all 24, the following equation is true. That AD times DQ equals to CD times DP. Repeat again, AD times DQ equals to CD times DP. So write it down. AD times DQ equals to CD times dP. Repeat again, according to all 24, the following equation is true. AD times DQ equals to CD times DP. AD equals to 1 times DQ. DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is. Times dP. dP is the opponent of the right dP out, and it is equals to the square root of 5 units in its length. So total according to all 24, we actually found out that 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to CD times square root of 5. Here we will divide this equation by square root of 5, and finally get that the missing side CD equals to 3 over square root of 5 units in its length. This is the missing side CD. That equals to 3 over square root of 5 units in its length. In the next step, we will implement the Pythagoras theorem on this right green triangle DCB. In order to find out the missing side CB. That is the only missing side. The area of the green shape, that is the area that we are looking for in this question, it is actually this right green triangle DCB. After we find out the left of side CB, the area of the green shape will be equal to the area of this right triangle DCB. It is equal to the base DC times the height CB over 2. That will be the answer to the question. This is actually the area of the green shape is the area of this green right triangle DCB. So we will implement the Pythagoras theorem on this right triangle DCB in order to find out the length of the missing side CB. So in this right green triangle DCB, Here by PT is the version for Pythagoras theorem. dB squared, that is the square of the hypotenuse, equals to CD squared plus CB squared. And again, in this right different triangle DCB, according to the Pythagoras theorem, the following equation is true. dB squared, that is the square of the hypotenuse, equals to CD squared plus CB squared. dB is square root of 5, and therefore dB squared is square root of 5 squared, that is 5, and it is equals to CD squared. CD is 3 over square root of 5, and therefore CD squared is 3 over square root of 5 squared, that is actually 9/5. And again, CD squared equals to 3 over square root of 5 squared, that is actually 3 squared, that is 9, over square root of 5 squared, that is 5. So in total, it is 9/5. Plus CB squared. CB is the missing side, so we leave it as it is. Here we will multiply 5 by 5 and then we divide it by 5 in order to have a common factor of this number. So we have 5 times 5 is 25 divided by 5. We multiply it by 5 and then we divide it by 5, so we change nothing. So in this part of the equation we have 25 over 5 equals to 9/5 plus CB squared. Here we subtract 9/5 from the equation and finally get that 25/5 minus 9/5 is 16/5. So 16/5 equals to CB squared. Here we take a root out of this equation and finally get that the missing side CB equals to the square root of 16, that is 4, over square root of 5. So I can find out that this is the missing side CB is equals to 4 over square root of 5 minutes in its length. Now it is very easy to see, to find out the area of this great shape, that the area of this great triangle DCB. Repeat again, the area of the green shape is actually the area of this green right triangle DCB. And the area of this green right triangle DCB equals to the base DC times the height CB over 2. Repeat again. The area of the green shape, that is the area that we are looking for in this question, is equals to the area of the green right triangle DCB. And the area of the green right triangle DCB, actually, that is actually true for the area of any triangle, equals to the base of the triangle that is DC times the height CB over 2. We already found out that the base CD equals to 3 over square root of 5 times CB. The height CB equals to 4 over square root of 5 divided by 2. Again, the base DC equals to 4 over square root of 5 and the height line CB equals to 4 over root of 5 divided by 2. 3 times 4 is 12, so in the numerator we have 12. Square root of 5 times square root of 5 is 5 divided by 2. So in total this expression equals to 12. We remove 2 to the denominator. So it is 12 times 5 times 2. So it is 12 times 5 times 2 is 10. 12 over 10 is 1.2 square units in its size. Repeat again, we should find out that the area that we are looking for this question, that is, they have this green shape, this is actually the right green triangle, DCB. In total it is equal to 1.2 square units in its size. So we finish with the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. A or B is a quarter circle, and therefore this is a right angle. The two radii of this semicircle are AO and OB. The radius BO equals to 2, and therefore the radius OO must be also equal to 2 units in its length. We already found out that point D is in the first method, that point B is the midpoint of the radius AO. That is to say, at point D, the radius AO has been bisected into two halves. The first half, it is 2 over 2, that is 1. The second half is also 1. So, all those things were already done in the first method. So, here we do a construction. That is to say, we will complete this quarter circle to a semicircle. Completed this quarter circle to a semicircle. We'll extend the radius BO by straight line. In the first method, we already found out that this is a chord PB, is the diameter of this semicircle. I'll not repeat all the same explanation. We already found out that chord PB is the diameter of this semicircle. in the first method, I only proved that the extended side CD must touch the semicircle or circle, it doesn't matter, at point P and not in any other point due to the contradiction to rule 5. And again, the extended side CD must touch the semicircle or circle at this point P and not in any other point. Now we don't have contradiction to rule 5 anymore. Why? Because we have peripheral angle BCP is equal to 90 degrees inside according to what is given in the equation. And peripheral angle BCP indeed subtend on chord PB, that is the diameter of the circle, exactly according to rule 5. In the first method, we only found out that this is the missing angle here, that it must be equal to 90 degrees inside according to rule 3. So I'll not repeat on the same explanation that we already done in the first method. This missing angle must be equal to 90 degrees inside. In this point O is the center of the semicircle, point P is the point of the semicircle itself, therefore OP is the radius of this semicircle, is equal to 2. This is the right triangle DPO. According to the Pythagoras theorem, we found out that the missing hypotenuse DP equals to the square root of 5 units in its length. We define this angle DPO, as alpha, and we focus on this right small triangle PDO. On the right small triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Therefore this furthest angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle PEB, this angle equals to alpha. This angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is the right triangle PDO. This right triangle PDO is similar to this big right triangle PCB. So why those two right triangles are similar to each other? Why the small right triangle PDO is similar to the big right triangle PCB? First of all, this is the angle alpha, that is a common angle that belongs to both triangles. Angle alpha belongs to the small right triangle PDO, and angle alpha definitely belongs to the big right triangle PCB. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if we prove that all the angles of this small right triangle PDO must be equal to all the triangles of this big right triangle PCB. And therefore those two right triangles are similar to each other according to angle similarity rule. So write it down, and you all know that this is the small right triangle PDO. Is similar. This is the sign of similar. To the big right triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PD of the small right triangle PDO or side PB of the big right triangle PCB is equal to side DO of this small right triangle PDO over side CB of this big right triangle PCB, and it is also equal to side PO of this small right triangle POD over side PC of this big right triangle PCB. So write it down. PO over PB equals to DO over CB equals to PO or PC. Okay, again, from the fact that the small right triangle PDO is similar to the big right triangle PCB, we will derive that the following relationship exists between their sides. We will derive that side PO of the small triangle over side PB of the big triangle equals to side DO of the small triangle over side CB of the big triangle, and it is also equal to side PO of the small triangle over side PC of the big triangle. PO equals to the square root of 5 over PB. PB in total equals to 2 plus 2, that is 4. This is the diameter of the semicircle. DO equals to 1 over CB. CB is the missing side, so we know what it is. And it is also equals to PO. PO is 2. Over PC. PC in total equals to the square root of 5 plus DC. And again, PC or CP in total equals to the square root of 5 plus DC. In total, you should all know that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other, so we get equation 1 from those two sides that are equal to each other. According to equation 1, we will get that square root of 5 over 4 equals to 1 over CB. So, write it down. According to equation 1, square root of 5 over 4 equals to 1 over CB. Here we will cross multiply this equation, and finally we get that according to equation 1, square root of 5 times CB equals to 4. Here we will divide this equation by square root of 5. And finally get that the missing side CB is equal to 4 over square root of 5 units in itself. This is the missing side CB. That is equal to 4 over square root of 5 units in itself. Those two sides of the equation are equal. To each other. So we get the equation 2 from those two sides that are equal to each other. So according to equation 2, we get that 1 over CB equals to 2 over square root of 5 plus DC. And again, according to equation 2, 1 over CB equals to 2 over square root of 5 plus DC. So here we first multiply this equation. So actually, not the correct equation. Those two sides of the equation are equal to each other. So we get the equation 2 from those two sides that are equal to each other. According to equation 2, we get that square root of 5 over 4 equals to 2 over square root of 5 plus DC. So that's it now. According to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. And again, according to equation 2, we actually found out that square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we of course multiply this equation. And we get that according to equation 2, 2 times 4 is 8, so 8 equals to the square root of 5 times square root of 5 plus DC. Here we will open the brackets of this of the equation. We get that according to equation 2, 8 equals to square root of 5 times square root of 5 is 5 plus square root of 5 times DC. So in total, according to equation 2, we actually found out that 8 equals to 5 plus square root of 5 times DC. Here we subtract 5 from this equation 2, and we get that according to equation 2, 8 minus 5 is 3, equals to 5 minus 5 is 0, so left only with square root of 5 times DC. Here we divide this equation by square root of 5, and finally get that the missing side DC is equal to 3 over square root of 5 units in itself. This is the missing side DC. This equals to 3 over square root of 5 units in itself. our task is to find out the area of this green shape. The green shape is actually the right triangle DCB. And again, our task is to find out the area of the green shape. The green shape is actually the area of the green triangle DCB. We know that the area of any triangle equals to the base of the triangle times the height over 2. We choose the base as DC, so it is equals to DC times the height, that is CB, over 2. And again, the area of the green shape, it is the area of the green triangle DCB, and the area of the green triangle DCB equals to the base DC times the height CB over 2. DC is 3 over root of 5 times CB. The height CB is 4 over root of 5 divided by 2. So the area of the green shape equals to the area of the green triangle DCB. And here we have 3 times 4 is 12 over square root of 5 times root of 5 is 5 over 2. So total this expression equals to 12 over, we'll move 2 to the denominator here. This is 5 times 2. So total this expression equals to 12 over 5 times 2, that is 10. 12 over 10 is 1.2 square units in size. So in both methods, we should find out that the area that we are looking for in this question, that is the area of this green shape, is equal to 1.2 square units in size. So we finish with the first question. The next step, we present you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle that intersects with this line, the right angle ACB, at those 2 points. So this is the right angle, angle ACB is the right angle. We know that line 7 CB equals to 1 unit in this line, line 7 CP equals to 4 units in this line. Again, our task is to find out the area of this circle. So in the drawing, we have from the common snap point P, we have 2 tangents to this circle, tangent PA and tangent PB. And therefore, we can implement here rule 2. So repeat quickly rule 2. According to rule 2, the lengths of 2 tangents from a common snap point to a circle are equal. In the drawing, we have a circle. This is the common snap point P. From this common snap point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB, or the length of tangent PA is equal to the length of tangent PB. Okay. We can implement rule 2 in our drawing. In our drawing, as I already mentioned before, this is the common snap point P. From this common snap point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So, write it down. If we focus on the common snap point P, we have 2 tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. P equals to PB according to rule 2. Tangent PA equals to tangent PB in its length. But it is given us the question that the length of tangent PB in total is equals to 1 plus 4, that is 5. So we can write here that the length of tangent PB is 5. And from this equation PA equals to PB equals to 5, we will derive that tangent PA must be also equal to 5 units in its length. P equals to 5. This is the tangent PA that equals to 5 units in its length. In the next step, we will implement the Pythagoras theorem on this big right triangle APC. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So the right triangle APC. Here by PT is the operation for Pythagoras theorem. The right triangle ABC according to the Pythagoras theorem. AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. Repeat again according to the Pythagoras theorem. In this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, it is 16. So in total, we shall find out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation and find again that 25 minus 16 is 9 equals to AC squared. Here we will take a root out of this equation and find again that the missing side AC is equal to the square root of 9 units. In its length, it is actually 3. The square root of 9 is 3. So the missing side AC equals to 4 units in its length. This is the missing side AC that equals to 4 units in its length. In the next step, we will define the center of this circle. This point is point O. We will define the radius of this circle as x. And we will join points O and B together by straight line. I remind you that point B is the point of tendency of tangent PB with this circle. So we join points O and B together by straight line. Point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of this circle, is equals to x according to our definition. The radius of OB is equals to x, the radius of OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. PB is a tangent, it is absolutely a straight line. So PB is a straight line. If you focus on the upper side of the straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 said that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point C? We have this angle that is the right angle, plus this missing angle. Total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say from point O, we will do perpendicular on side AC. Again, from point O, that is the center of this again, we will do perpendicular on AC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point M. By doing this construction, we get the deal quadrilateral OMCB. Inside quadrilateral OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total, the must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral OMCB, we have 4 angles, and therefore we can relate to quadrilateral OMCB as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OMCB, side BC must be equal to the opposite side OM. But BC is 1, therefore the opposite side OM must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the sum rectangle OMCB, side OB must be equal to the opposite side MC. But OB is x, therefore the opposite side MC must be also equal to x units in its length. What is the length of this missing line segment? AM. AM in total equals to AC minus MC. So, moving on. The missing side AM is equal to AC minus MC. So in total, the missing side AM equals to AC, that is 3. AC is 3. Minus MC. We just now found out that MC equals to x. So in total, we found out that AM equals to 3 minus x units in its length. In the next step, we will join points O and A together by a straight line. Point O is the center of this circle, point A is the point of the circle itself, therefore OA is the radius of this circle, is equals to x. So in the next step, we will implement the Pythagoras theorem on this right green triangle, triangle OAM. So in the right green triangle OAM, here by PT is a version for Pythagoras theorem, so in this green right triangle OAM, according to the Pythagoras theorem, AO square, that is the square of the hypotenuse, equals to AM square plus OM square. And again, in this right triangle OAM, according to the Pythagoras theorem, the following equation is true. OA squared, that is the square of the hypotenuse, equals to AM squared plus OM squared. AO equals to x, therefore AO squared is x squared. And it is equals to AM squared. AM is 3 minus x, therefore AM squared is 3 minus x squared plus OM squared. OM is 1, therefore OM squared is 1 squared, this is 1. So in total we found out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, this is 9, plus x squared, minus 2 times 3 times x, that is minus 6x, plus 1. Here we have x squared on both sides of this equation, so x squared will get cancelled. After we cancel x squared in this side of the equation we have to leave nothing, this is to say 0, while on the other side of the equation we have here 9 plus 1 is 10, minus 6x. So in total, we should find out that 0 equals to 10 minus 6x. Here we will add 6x to this equation and get that 0 plus 6x is 6x equals to 10. So 6x equals to 10. Here we will divide this equation by 2 and finally get that 6x over 2 is 3x equals to 10 over 2 is 5. So in total, we should find out that 3x equals to 5. Here we will divide this equation by 3 and finally get that x equals to 5 thirds. X equals to 5 thirds units in its name. X is the radius of this semicircle, x is the radius of this circle. Our task is to find out the radius of this circle. Actually we know that the radius of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is pi x squared. So it is pi times x squared. X is 5 thirds, and therefore x squared must be 5 thirds squared. So it is pi times 5 thirds squared. 5 thirds squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total we found out that the area that we are looking for this question, that is the area of this circle, it is equals to either 25 pi over 9 square units in size, or in terms of numbers, it is equal to 8.73 square units in size. Repeat again, we should find out that the area that we are looking for this question, that is the area of this circle, it is equal to either 25 pi over 9 square units in size, or in terms of numbers, the area of this circle equals to 8.73 square units in size. So we finish with the second question. The next step of the lecture, we'll start with the repetition of the solution of the first question and then repeat on the solution of this second question. In the first question, our task is to find out the area of this green shape. The green shape is actually the right green triangle DCB. So we have to find out the area of this green right triangle DCB. In the drawing, we have a quarter circle. AOB is a quarter circle. This is side OB. This equals to 2 units in its length. This is line 70 AD. Is equals to line 70 O. This is again BCD. This is the right angle. So we have to find out the area of this green shape. This is actually the area of this green right triangle DCB. So we start with the first method. First of all, it is given us the question that AOB is a quarter circle, and therefore this is the right angle. Likewise, OB equals to OA, they are both the radii of this quarter circle, and therefore they are equal to each other. But the radius OB equals to 2, and therefore the radius OA must be also equal to 2 units in its length. The radius OA is been bisected into 2 halves at point D. So the first half AO must be equal to 2 over 2, that is 1, and the second half of the radius AO must be also equal to 1 unit in its length. So in this right triangle DOB, we can implement the Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the scores of the perpendiculars. So in this right triangle DOA, dB squared, that is the square of the hypotenuse, equals to DO square plus OB square. And again, this right triangle DOB, according to the Pythagoras theorem, the following version is to the dB squared, that is the square of the hypotenuse, equals to DO square plus OB square. dB is the missing side, so we leave this it is. So it is dB square equals to DO square. DO is 1, therefore DO square is 1 squared, it is 1, plus OB square. OB is 2, therefore OB square is 2 squared, it is 4. So in total, we actually found out that dB square equals to 1 plus 4, that is 5. So dB square equals to 5. Here we took a root out of this equation and found out that the missing hypotenuse dB is equal to the square root of 5 units in its length. This is the missing hypotenuse dB. This equals to the square root of 5 units in its length. In the next step, we did the construction. That is to say, we completed this quarter circle to a circle. We extended the radius BO by side line until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point P. In the radius, it is absolutely straight line. When you extend the straight line by straight line, the result BP must be also a straight line. BP is a straight line that touches the circle at those 2 points P and B. And therefore, BP is a chord. BP is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore, BP is the diameter of the circle. In the next step, we extended the radius AO by side line until it touches the circle at this point. So we define the touching point of the extended radius AO with this circle. This point is point Q. Point O, when you extend the side line by side line, the result AQ must be also a straight line. And therefore, AQ is also the diameter of this circle. It equals to 4 units in its length. Why? Because point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. It equals to 2. And if the radius is 2, the diameter must be equal to 4, of course. The diameter AQ equals to also 4 units in its length. In the next step, we extended side CD of this DCB by side line until it touches the circle. And actually prove that the extended side CD must touch the circle at point P and not in any other point. Why? Because if we assume that the extended side CD will touch the circle at this point, point N, then we get contradiction 2 or 5. Because we have here peripherical BCN, this equals to 90 degrees inside according to what is given as the equation, and still peripherical BCN subtend on code BN. That is definitely not the diameter of the circle. Why BN is not the diameter of the circle? Because it doesn't pass from point O. That is the center of the circle. Therefore, any code that doesn't pass from the center of the circle cannot be the diameter of the circle. But according to rule 5, any peripherical that is equals to 90 degrees size, like this peripherical BCP, that is the right angle, must subtend on the diameter of the circle. But peripherical BCP subtend on code BN, that is definitely not the diameter of the circle. So due to the contradiction to rule 5, we conclude that the extended side CD cannot touch the circle at point N. Likewise, we assume that the extended side CD will touch the circle at this point, point M. According to our assumption, we have a peripherical BCM that is equals to 90 degrees inside, and it's subtend on code BM. Code BM is definitely not the diameter of the circle because of the fact that code BM doesn't pass from point O, that is the center of the circle. Any code that doesn't pass from the center of the circle cannot be the diameter of the circle. So we have a contradiction to rule 5 because we have peripherical BCM that is equals to 90 degrees inside, and still it doesn't subtend on the diameter of the circle. So due to the contradiction to rule 5, we derive that the extended side CD cannot touch the circle at this point N. And therefore, the extended side CD must touch the circle at this point P and not in any other point. Otherwise, we have contradiction to rule 5. Now we don't have contradiction to rule 5 anymore. Why? Because we have peripherical BCP, this is equals to 90 degrees inside, and indeed is subtend on code PB, that is the diameter of the circle, exactly according to rule 5. So in this, we know that PB is the diameter of the circle, so PB is the diameter, it is absolutely straight line. So if we focus on the upper side of the straight line PB at point O, is the sum of the angles must equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angle we have at the upper side of PB at point O? We have this angle that is the right angle plus this missing angle, and total the sum of those two angles must equal to 180 degrees according to rule 3. Therefore this missing angle must equal to 90 degrees in size. So in the right triangle PDO, point O is the center of the circle, point P is the point of the circle itself, so therefore P is the radius of the circle, that is equals to 2. The hypotenuse PD must be equal to the square root of 5 units in itself and only to the Pythagoras theorem. Those two materials can go into each other. The hypotenuse DB equals to the square root of 5, therefore the hypotenuse DP must be also equal to the square root of 5 units in itself. Okay. So here we can implement rule 24 in our drawing. Repeat quickly on rule 24. According to rule 24, rule 24 is drawn in any circle, so in any circle, if chord AB intersects with chord CD at point O, then the following equation is told AO times VO equals to CO times VO. In the drawing we have a circle, this is chord AB that intersects with chord CD at point O. In this drawing the following equation is told that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 24 in our drawing. Why put in our drawing? Chord AQ intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. So all the requirements of rule 24 are satisfied, and therefore we can implement here rule 24. Why CP is the chord? Because we extended the straight line CD by straight line, and therefore the result CP is also a straight line. It is a straight line that touches the circle at 2 points, C and P, therefore CP is a chord. Likewise, AQ is the diameter of the circle, and therefore it is definitely a chord. So chord CP intersects with chord AQ at point D. Chord AQ intersects with chord CP at point D. So all the requirements for rule 24 are satisfied, and therefore can implement rule 24. According to rule 24, the following equation is called that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. And again, according to rule 24, AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total is 1 plus 2, that is 3. And it is equals to CD. CD in the missing side, so it is times DQ. DQ is equal to 5. So in total, we should follow that 1 times 3 equals to CD times equal to 5. 1 times 3 is 3, so 3 equals to CD times equal to 5. Here we divided this equation by equal to 5 and find out that if I found out that the missing side CD equals to 3 or equal to 5 minutes in Islam. This is the missing side CD equals to 3 or equal to 5 minutes in Islam. So this is the real R-time DCB. You know that the diameter DB equals to the square root of 5 minutes in itself. We just right now found out that CD equals to 4 over square root of 5 minutes in itself. So we implemented the Pythagoras theorem on this in R-time DCB in order to find out the missing side CB. According to the Pythagoras theorem, in this R-time DCB, DB squared, that is the square of the hypotenuse, equals to CD squared plus CB squared. And again, the R-time DCB, according to the Pythagoras theorem, DB squared, that is the square of the hypotenuse, equals to CD squared plus CB squared. The hypotenuse DB equals to the square root of 5, therefore DB squared equals to the square root of 5 squared, that is 5. And it is equals to DC squared. DC is 3 over square root of 5, and therefore DC squared is 3 over square root of 5 squared, that is actually 9/5 plus CB squared. CB is the missing side, so it is. So to that, I should find out that 5 equals to 9/5 plus CB squared. Here we multiply it 5, and then we divide it by 5 in order to become a factor of this number. So 5 times 5 is 25 divided by 5. And it equals to 9/5 plus CB squared. Here we subtract 9/5 from this equation and find out that 25/5 plus 9/5 is 16/5 equals to CB squared. Here we take out of the equation and find out that the missing sign CB equals to the square root of 16, that is 4, over square root of 5. This is the missing sign CB, that is equals to 3 over square root of 5 minutes in itself. Our task is to find out the area of this green shape. The green shape, it is actually the green right triangle DCB. So we have to find out the area of this green right triangle DCB. Okay, again, the area of the green shape is actually the area of the green right triangle DCB. And the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this green right triangle DCB equals to the base DC times the height CB over 2. So again, the area of the green right triangle DCB equals to the base DC times the height CB over 2. DC is 3 over square root of 5, CB is 4 over square root of 5. And again, DC is 3 over square root of 5, CB is 4 over square root of 5 divided by 2. 3 times 4 is 12, square root of 5 times square root of 5 is 5 divided by 2. So this expression equals to 12 times 5 times 2. We just move 2 to the denominator. And 12 times 5 times 2, 5 times 2 is 10, so this expression equals to 12 tenths. 12 tenths is 1.2. So if you found out that the area that we're looking for this question, that is the area of this green shape, in total is equal to 1.2 square inches in size. So we finish with the first method. The next step, I repeat on the solution according to the second method. We find out the area of this green shape according to the second method. Repeat on the solution. In the first method, we know that the radius OB equals to 2, it is equals to the radius OA, and it is also equals to 2. At point D, the radius AO is intersected into 2 halves, each half equals to 1. This is the right angle because AOB is a quarter circle. So here we extended, first of all, this angle equals to, we extended, first of all, we completed this quarter circle to a semicircle. We extended the radius BO by side line and it touches the circle at this point. We find the touching point of the extended radius BO with this semicircle. This point is point P. We only found out that in the first method that PB is the diameter of the semicircle and also the diameter of the circle. And in the first method, I already proved that when we extend CD by side line, it will touch the circle or semicircle at point P and not in any other point because of the contradiction to rule 5. The extended side CD must touch the circle at point P and the semicircle at point P and not in any other point. So repeat again that this is the right angle according to rule 3. So the right angle POB, the hypotenuse PD equals to the square root of 5. We only found out in the first method that the hypotenuse PD equals to the square root of 5, so I want to repeat here the same explanation. We just have to implement the Pythagoras theorem on this right angle PDO. So here we have the right angle DPO. We define this angle DPO as alpha, so this angle equals to alpha. In the right angle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this part of this angle must be equal to 90 degrees minus alpha. Where equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, this is equal to 180 degrees, that is the sum of the angles in a triangle. Therefore this part of this angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this part of this angle must be equal to 90 degrees minus alpha according to the sum that states that the sum of the angles in any triangle is equal to 180 degrees. The next step will prove that the right triangle PDO is similar to the big right triangle PCB according to angle similarity rule. So the right triangle PDO is similar to the big right triangle PCB. First of all, this is angle alpha, this is a common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and therefore they are equal to each other. So if you prove that all the figures of this small right triangle PDO correspond equal to all the figures of this big right triangle PCB, and therefore those two right triangles are similar to each other according to angle similarity rule. And again, if you found out that the small right triangle PDO is similar, this is the similar to the big right triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side PO of the small triangle or side PB of the big triangle equals to side DO of the small triangle or side CB of the big triangle, and it is also equal to side PO of the small triangle or side PC of the big triangle. PO is equal to 5, PB is 4, DO is 1, CB is the missing side, so it is. PO is 2, and PC in total, PC equals to PD that is equal to 5 plus DC that is the missing side. So in total, we should found out that PC equals to the square root of 5 plus DC. So in total, we should found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other, so in case the question mark from those two sides are equal to each other. That is to say square root of 5 over 4 equals to 1 over CB. Square root of 5 over 4 equals to 1 over CB. Here of course multiplies the equation 1, if I found out that 4 equals to square root of 5 times CB. Here we divided this equation by square root of 5 and found out that the missing side CB equals to 4 over square root of 5 units in its length. This is the missing side CB. This equals to 4 over square root of 5 units in its length. Those two sides of the equation are equal to each other, so I get the equation 2. from those two sides that are equal to each other. According to equation 2, we will get that square root of 5 over 4 equals to 2 over square root of 5 plus dc. And again, according to equation 2, we shall find out that square root of 5 over 4 equals to 2 over square root of 5 plus dc. Here we cross multiply this equation, if I found out that 2 times 4 is 8, and it is equal to the square root of 5 times the square root of 5 plus dc. So 8 equals to, we open the brackets of this expression, so it is square root of 5 times square root of 5, that is 5, and square root of 5 times dc, square root of 5 times dc. Here we subtracted 5 from this equation, and I found out that 8 plus 5 is 3 equals to the square root of 5 times dc. Here we divided this equation by the square root of 5, and finally found out that the limit inside dc equals to 3 over square root of 5 units in itself. This is the limit inside dc, that equals to 3 over square root of 5 units in itself. Our task is to find out the area of this green shape. The area of the green shape equals to the area of the green right triangle DCB. The area of the green right triangle DCB equals to the base DC times the height CB over 2. But again, our task is to find out the area of the green shape. The green shape is the right triangle DCB. So we have to find out the area of the green right triangle DCB. The area of the green right triangle DCB equals to the base DC times the height CB over 2. DC is 3 over square root of 5. BC is 4 over square root of 5 divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5, and we have to divide it by 2. Here we move to the denominator, and actually this expression equals to 12 over 5 times 2, that is 10. So it is 12 over 10, or 12 tenths. That is 1.2 square inches in size. So in both methods, we actually found out that the area of this green shape, that is the area that we are looking for in this question, it is equal to 1.2 square inches in size. So we finish with the first question. In the next step, I'll repeat on the solution of the second question. On the second question, our task is to find out the area of this circle. So in the drawing we have a circle that intersects with this right triangle ACP, those 2 points. This is line 7 BC, this is equals to 1. This is line 7 PC, this is equals to 4. This is right angle ACP. This angle is right angle. In the drawing we have also tangent PB, that is tangent to this circle at point B, and tangent PA, that is tangent to this circle at point A. Again, our task is to find out the area of this circle. So here, from the current start point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to all 2, they are equal to each other. That is to say, PA equals to PB. And again, according to all 2, tangent PA equals to tangent PB in its length. But PB, tangent PB, the area of tangent PB in total is 1 plus 4, that is 5. So we can write down that tangent PB equals to 5 units in itself, and for this equation PA equals to PB equals to 5, we know that PA also equals to 5 units in itself. This is tangent PA, that is also equals to 5 units in itself. In the next step, we created the quadratic theorem on this right triangle ACP. First of all, this is given us a equation, this is the right triangle. So in the right triangle ACP, AP square, that is the square of the hypotenuse, equals to AC square plus CP square. And again, the right triangle ACP, according to the quadratic theorem, AP square, that is the square of the hypotenuse, equals to AC square plus CP square. AP is 5, therefore AP square is 5 square, that is 25. And it is equal to AC square. AC is the missing side, so it is, plus CP square. CP is 4, therefore CP square is 4 square, that is 16. So in total, we should all know that 25 equals to AC square plus 16. Here we subtract 16 from this equation, and we found out that 25 plus 16 is 9, equals to AC square. Here we took out of this equation, and we found out the missing side AC equals to 3 units in its length. This is the missing side AC, it equals to 3 units in its length. In the next step, we define the center of this circle. This point is point O, and the Point B is the point of tendency of tangent PB in this circle. In the next step, we join points O and B together by side line, and we define the radius of this circle as x. Point O is the center of this circle, point B is the point of the circle itself, therefore OB is the radius of this circle. This is equals to x according to our definition. The radius OB is equals to x, the radius OB is known to point B, that is the point of tendency of tangent PB with this circle. And then your radius is known to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. PB is a tangent, this is absolute straight line. So if you focus on the upper side of the straight line PB at point C, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the areas from one side of the straight line is equal to 180 degrees. So which areas we have the upper side of the straight line BP at point C? We have this angle, this is right angle, plus this missing angle, in total the sum of those areas must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we did the construction, that is to say from point O we do perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AM, from point O and AC. This point is point M. By doing this construction, quadrilateral OMCB. Quadrilateral OMCB, we have 1, 2, 3 areas. The sum of 3 areas is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees. According to the rule, that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in size. So in quadrilateral OMCB we have 4 angles, and therefore quadrilateral OMCB we can relate to quadrilateral OMCB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OMCB, side BC must be equal to the opposite side OM. But BC is 1, therefore the opposite side OM must be also equal to 1 in itself. Likewise, according to the sum rule, in the sum rectangle OMCB, side OB must be equal to the opposite side MC. But OB is x, therefore the opposite side MC must be also equal to x units in itself. What is the length of this missing line side AM? AM equals to AC minus MC. Again, AM equals to AC minus MC. So AM equals to AC, that is 3, minus MC, that is x. So in total, AM equals to 3 minus x units in itself. In the next step, we will join points O and A together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, that equals to x. In the next step, we implemented the Pythagoras theorem on this right triangle AOM. Right triangle AOM. AO squared, this is the square of the hypotenuse, equals to AM squared plus MO squared. And again right triangle AOM, according to the Pythagoras theorem, AO squared, this is the square of the hypotenuse, equals to AM squared plus MO squared. AO is x, therefore AO squared is x squared, and it is equals to AM squared. AM is 3 minus x, therefore AM squared is 3 minus x squared, plus OM squared. OM is 1, therefore OM squared is 1 squared, that is 1. So in total, if you found out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, plus 2 times 3 times x, that is minus 6x plus 1. We have x squared on both sides of the equation, so x squared can cancel. After we cancel x squared on this side of the equation, we have to have nothing, that is to say 0. While on the other side of the equation, we have 9 plus 1, that is 10, minus 6x. So in total, 0 equals to 10 minus 6x. Here we added 6x to this equation, and found out that 6x equals to 10. Here we divided this equation by 2. 6x over 2 is 3x, and 10 over 2 is 5. So 3x equals to 5. 3x equals to 5. Here we divided this equation by 5 and found out that x, that is the radius of this circle, equals to 5/3. Our test is to find out the area of this circle. The area of any circle equals to pi times the radius of this circle squared. And therefore, the area of our circle is equal to pi times the radius of our circle squared. The radius of our circle is x, so the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. But x is 5/3, therefore x squared is 5/3 squared. So pi x squared is pi times 5/3 squared. So it is pi times 5 squared. 5 squared is 5, pi times 5 thirds squared. 5 thirds squared equals to 5 squared is 25, or 3 squared is 9. So in total, if you want to know that the area that we're looking for, this question, that is the area of this circle, equals to either 25 pi over 9 square units inside. So in terms of numbers, the area of this circle equals to 8.73 square units inside. Okay, thank you very much.